Right. So now let's see what is the next algorithm, right? So Gauss-Newton, in a sense, they propose that algorithm when m is greater than n. The algorithm is for when number of equation, nonlinear equation is more than n, right? Because we use this D matrix and idea of a least square. Now m is greater than or equal to n, of course. Then the next group of people were Newton-Raphson. So what they did is that they just do it for a special case for m equal to n, right? So Newton, so I said Gauss-Newton, then become Newton-Raphson. Newton did it for n equal to 1, and Raphson did it for n greater than 1. So in general, they did for m equal to n, number of equation and number of unknowns are the same, right? Okay, so everything, the idea, the atomic criterion, everything is the same. The sudden difference is that when m equal to n, right, then D matrix is gonna be a square. Remember, D was m by n matrix, right? So if D was m by n matrix, then it's a square. Therefore, that least square solution that we have seen. So let me write it here. Let me write it here. This D of f of x of k transpose D of f of x of k inverse D of f of x of k. This is the pseudo inverse, right? Left inverse of a matrix, right? Very good. So this one is going to be replaced by this. And that's what we have. The update equation becomes nicer. That's it, right? But unfortunately, since the problem is the same, it's only the matrix is a square now. But so it shares the same shortcoming as a Gauss-Newton method, right? The Newton-Raphson techniques share the same shortcoming. If the D matrix does not have a linear independent column, then this matrix is not invertible, and this update doesn't really exist. So I wrote here the Newton developed for n equal to 1, and that's why you see a lot of Newton methods for when you have actually a scalar value function, and also the x is n by 1 actually, right? Or sorry, is 1 by 1. So like this one, for example, you want to solve this equation, t ln of t is equal to 2, something like that, right? And Raphson developed that for n greater than 1, which t is, for example, a scalar. Okay. So now we want to see how we can get rid of this shortcoming. And that's where the Levenberg algorithm, LM method, comes into the picture. Okay. So the idea behind LM is by addressing the shortcoming or the problem that Gauss-Newton method has. So in a sense, what we want to do is that we want to again use them affine approximation and then use the least square in the step 2 to find the next estimate. But I want to make sure that my current estimate and the solution always stay within a boundary, right? Always, I want to make sure that this quantity is always small, right? Let me just make it like this. This is what I want to make sure. Okay, good. So remember when we talked about the Tikhonov regularization, and also when we were talking about the multi-objective least square, right? We actually motivate this idea in a constraint least square case as well. When you write this this square problem as a multi-objective case, you have this Tikhonov regularizer, right? Sometimes you call it a trust parameter, right? For this case, you want to minimize this norm, right? That's your goal. But at the same time, this is the second objective you have. So this is called a primary objective, right? This is the secondary objective that you have. You want, as I wrote here, we don't want to go far from the current estimate. We want the current estimate and the solution to be actually near each other, or from the solution. It's better to want these two actually to be close to each other, right? Okay. So if lambda is 0, if we go back to the Gauss-Newton, right? So let's think about that. That's why I wrote here, if lambda is 0. If lambda is small, right, then we are primarily minimizing the first term, right? If lambda is 0, actually this term doesn't exist. But if lambda is small, we are actually minimizing this term primarily. Well, then we are actually, again, we are letting the norm of x minus x of k to be still very big. We are letting this to happen. So this is an issue. This is still an issue, right? When lambda is big, right, we make sure that these two quantities, because we are primarily minimizing this when lambda is big, then we make sure that this quantity is very small. So we are happy. Then the affine approximation is accurate. If when lambda k is big, then affine approximation is accurate. Then we are doing something correctly. We are actually, next step is making sense, because the least square is actually the correct estimate, right? Okay, good. Also, in a sense, when we talk about this multi-objective least square, remember the way we solved that? We put it in the form of this stack matrix. And that stack matrix, we proved that it should have a linearly independent column. But in the case of Tikhonov regularization, it always has a linearly independent column, right? Let's take a look at this here. I'm gonna write this equation that I have, this one. I will call it equation 1 in this form, right? In a form of 2. Well, in a sense, after you find the affine approximation, right? So you see, let's see. I want to write this one in a sense ax minus 3. This is like ax minus 3, right? This is nothing but ax minus b, because after we, this is ax minus 3 exactly. This is affine approximation. This is not the original nonlinear square, right? Plus lambda k x minus x of k square. Okay, good. So in a sense, I have to identify A. But wait, I did identify A. I know that A is like that. I proved it before. And whatever is left was B. So this is exactly like the stack least square technique that I used in the past. This is A. This is going to be root lambda K, like before, like a Tikhonov regularization. This is B. And this is root lambda K times X of K. This one, this is a new B, right? Good. And this is the other B that I had. The other B that is left is this one, right? So like a stack least square. I will put a link in the multi-objective least square video, right? To make sure that you actually recall this equation. I actually talked about that in a multi-objective and also constraint least square case, right? Good. But thanks to this I, this stack matrix, let's call it A tilde, has a linearly independent columns, even if d of f of x of k, even if this has a linearly dependent columns, right? Thanks to this I, right? We talk about this in multi-objective case. Okay, so this A tilde always has a linearly independent columns. So wait, thanks to this regularization of this trust parameter, we make sure that this x and x of k are always close to each other. And we make sure that this stack matrix has a linear independent columns. So we actually solve all the shortcoming of the Gauss-Newton method. Okay. So now let's see what is this x of k plus 1. Exactly the same thing, right? Now you're gonna solve A tilde. This is B tilde. A tilde transpose A tilde inverse A tilde transpose B tilde, right? That's what you're gonna solve. If you put that together and calculate that, you get to this new update equation, which this one we have seen it in the past in the multi-objective case. You have this lambda k as well. This lambda k helps us that this inverse always exists, and that's why I say always exists. Okay, again, like before, we want the solution to repeat itself. One of the stopping criterion is that this x of k plus 1 is similar to x of k, right? Means that the solution again repeats itself. We are converging to the solution. If this must happen, then regardless of condition on B, this always exists, right? So therefore, we want this term to be 0, right? If we want this term to be 0, we want this optimality condition again to hold. This 2 is not necessary, but it's a form of optimality condition that we drive, okay? So that's a stopping criterion. Good. More about that at the end of the video. But how to choose this lambda k? If lambda k is too small, this xk plus 1 and xk might be very different from each other. If lambda k is too small, then there is no guarantee that this quantity is actually small, right? Then affine approximation is not a good approximation. I will write it here. Affine approximation is not good approximation. If lambda k is too big, great. The affine approximation is good approximation, but this xk plus 1 and xk, the difference between them will be really small at each iteration. So we are actually converging very slowly, right? So it will take a lot of iteration to converge, right? So if you set the maximum number of iteration to be a small value, you might never converge. And also it takes long time to converge. So that one also is not really good, right? So that's what I explained here as well. The objective reduced. However, at each iteration, xk plus 1 and xk are really close. So it takes many iterations to get to a solution. So in a sense, there are many ways to choose this lambda k, right? But one simple way is this. So you are going to choose with some value for a lambda, initial value. You call it lambda 1. Let's say you choose 1, right? So you construct xk plus 1 using the current value of lambda and check to see if the value of the objective is reducing or not, right? So you have some optimality condition at each iteration. You check that one for the so xk plus 1 also you check this. If it's going down, you accept this. You accept the new point and you decrease the lambda, right? You multiply lambda, you call lambda 2 to be, for example, 0.8 times lambda 1, or any value you like. Call like beta 1, right, to be equal to 0.8, and you write beta 1, anything you like, right? But if actually the objective is not reducing, then you know that you have to choose a lambda to be a bigger value. Why is that? If objective is not reducing, the estimate, the next estimate is not a good estimate. This means that something went wrong with that affine approximation, right? If something went wrong with that affine approximation, this means that this condition is failing. This condition is failing. This affine approximation, this means that this condition is failing. So you're gonna go ahead and multiply this lambda 2 by another quantity, beta 2 times lambda 1, right? Where this beta 2, for example, is 2, right? Now lambda gets bigger. And you keep doing this in a loop, right? Until some sort of convergence happen, some sort of a stopping criteria. And that's what I explain actually here. If the objective has not decreased, usually lambda is too small. So do not update xk plus 1, right? So we had the previous value of the x of k, right? And we increase the lambda, okay? So what's the stopping criterion? I talked about that. One of them is the optimality condition, which we want it to be a small. The other one is that this quantity, because we are trying to solve this f of x equal to 0, right? So norm of f of xk plus 1, in a sense, to be very small, right? That's another optimal condition. Another one is that x of k minus xk squared to be small, or the norm of that is small. This is similar to the optimality condition, right? This is similar, but there are many ways. And also another one is the maximum number of iteration. Of course, maximum should be always there. Maximum number of iterations, right? So these are optimality conditions that are shared between many different nonlinear least square techniques, right? So that's it for this video. Thank you so much for watching that. In the next video, I'm going to talk about nonlinear least square for the convex function. Okay, thank you so much.